Hello, my name is Ben Davidson with Space Weather News, and I want to thank you for watching this third and final infomentary film we're putting out in August 2019. The professor and I hope you enjoy it, and that you come away informed. Let's not waste any time and get right to it. This topic is going to be difficult enough without a political discussion, so let's wipe it off the table now. This is the air we breathe, the water we drink, the soil in which we grow our crops. That right there is enough of a reason not to pollute it. We are in fact 100% anti-pollution. We favor stronger restrictions on polluters and even things such as retroactive cleanup provisions and other penalties. We do hope that this video can remain outside of any sort of policy confusion such as this. It is about nothing other than a scientific point that supersedes all of climate science. It is important that we establish, first and foremost, that indeed, the entirety of climate science is constructed upon a few key foundations. If there's one problem or multiple problems, it jeopardizes the whole. Thousands of studies out there don't individually go and recreate a model of the Earth. They use base models and widely accepted assumptions, and these models were created to make those studies easier. This is what the scientists are supposed to be doing. The problem is that the model has three insurmountable and relatively obvious flaws, and those are shared at the foundational level of all of those papers, the ones making up the 97%. And they have the practical effect of rigging the studies to come out one way. Now here's a way to think about modern climate science. It's like a mansion, a skyscraper, constructing a megacity. But like every structure, it has its foundations. They must be built strongly and without missing steps, or you do risk the stability of the entire structure above. Well, what happens when a leviathan like climate science is built on entirely poor foundations? Even with pristine glass and offices and apartments and restaurants gracing the walls above the ground in the great megacity of climate science, the foundations are flawed, and because of that, all of this must collapse. You should be skeptical of the claim as laid out. It is extreme and requires proof for an academic mind to cradle. But incredulities and skepticism aside, you should be able to grasp the simple foundational concept to which we alluded. If the foundations fail, it doesn't matter how many scientists and thousands or millions of papers stand upon them, they will all fall. I would argue that to deny this is indicative of a non-academic mind, and so under this accord, we proceed.
This truly is an accurate way, very, arguably oversimplified, true, but this is a 100% accurate way to write the equation for climate change. You have what the Earth is naturally doing, you have what humans are doing, and the total of that is the total climate change. Very, very simple. When it comes to natural variability, that's things like the sun, things like albedo of the planet, that's how much light gets reflected off of white clouds or ice versus gets absorbed and integrated and transformed into heat eventually. Volcanoes in how they block out sunlight. And, of course, Milankovitch cycles, precession, in both axial and the apsidal precession. So all of these things would be part of natural variability. The human changes to the planet are mostly chemical in terms of carbon emissions, things like that, deforestation, urban heat islands, and other smaller localized things like that. And true enough, If you get all of these pieces correct, then everything will work. But the problem is with what I've circled there at the bottom left. If we don't have the natural variability portion of this equation down firm, then by definition we can't get the human changes portion correct.
For the entire history of modern climate science, the sun's influence has been described by total solar irradiance, a measure of the sun's effect on the upper atmosphere. It looks like this when charted with an 11-year up and down due to the fact that the sun has an 11-year sunspot cycle. When there are more sunspots, we get more irradiance at Earth. This variation is small, however, only 0.1% over that 11-year cycle. That's a change of just 0.1%. Even during the sun's ultimate low points, called grand minima, which occur every few centuries, we are barely looking at 0.2% lower energy received. This is not a lot of variability, and furthermore, since the upper atmosphere thermal coupling, the heating due to the sun, slowly trickles down through the stratosphere and the lower atmosphere, with lots of mixing, there has been a long-standing presumption that the sun's output has little effect on climate change. But now here is where the problems begin. Do you see all these spikes downward? Well, some of those are things like the Venus transit, or long, full eclipses, but the vast majority of the spikes down are major solar flare events on the sun. An excellent example happened in early September 2017. The largest solar flares in 12 years began pounding Earth with X-ray radiation, high-energy protons, and they induced electric currents through the atmosphere and the ground. It was a titanic surge of energy to Earth, but this is what showed up on the charts, a drop in energy. This is wholly backwards. In climate models, these events show that the sun dropped energy, so since it did not, the equation for climate change must increase the human effects to balance out the equation. Even worse, the actual increase in energy from the sun is missing, and so that energy, when accounted for in climate models, also gets blamed on humans. In terms of ill-gotten gains, that's a twofer. But how could the upper atmosphere show a drop in energy received from the sun during such incredibly powerful events? Well, the answer is simple. Not all of the sun's energy is received at the upper atmosphere. In order to properly understand the failings of total solar irradiance, we must fully understand the expanse of solar forcing. There are three basic ways the sun's energy arrives at Earth. Energy waves like X-rays, ultraviolet, and obviously the visible light we see. The sun puts out the particle solar wind 24 hours a day, and major solar flares can increase the particle burst by up to hundreds or thousands of times. The Earth is also directly connected to the sun magnetically. Earth's magnetic field is literally entwined with the sun's, allowing for a full exchange of energetic particles that bypasses Earth's own protective magnetic shell. There are also the particle effects of cosmic rays. These are generally atomic nuclei that break out into particle cascades of various nature, electric charge, and interaction potential. These generally come from distant supernova or other energetic events in distant space.
Part of the problem is that when people do correlations on the 11-year solar cycle, there's a whole lot of things that vary. The sunspot number, 10 centimeter radio flux, the magnesium ion line, the total solar irradiance, but also we've got the flux coming from the solar wind, and it has lots of day-to-day variations, as do the geomagnetic disturbances on the Earth, and also there's an effect on the galactic cosmic ray flux.
When we consider the conundrum of the total solar irradiance drop during major solar flares, we must recognize that the changes in solar output cannot be measured in simple percents, but require larger scales of comparison.
In X-rays, we see 100 to 100,000 times increase over minutes to hours. Solar wind, phenomenal increases. Again, we're talking orders of magnitude. In terms of the energetic particle flux, specifically the protons, the high energy protons, those can have 10 to 1,000 times increase. It's difficult to say exactly how much of an effect those have on the ionosphere potential. that translated or transformed down into the global electric circuit and things like that. Now, despite everything you see up there at the top, the official solar heating influence of the event is in the negative. So here we have phenomenal increases. These are the biggest deliveries of energy from the sun to Earth, and they show up as 0.05 to 0.3% decreases in the amount of energy the sun has given us. Well, it results in climate change, and you can't account for it in the natural variability because you're only looking at TSI. So you have all of that real forcing, and where do you have to put it in the equation? You have to put it on the human changes. So true enough, the actual difference is attributed to human-induced global warming. Not just what the sun actually does, but the false decrease that is shown in the actual solar input. And so what that means is for the history of climate science, what is more than 140 years of solar flares and CMEs pounding our planet, not just missing, not just showing up as negative solar energy, but they are included on the human side of that equation. By definition, this is a big problem. And then you realize that the problem when you're looking at the period of global warming might be an even more extreme case. This paper came out, and it's been recited a number of times, although I don't think any of the citations really do anything to further the point made in the original work, and none of the original authors are in the subsequent ones, so I figured I'd go back to where it actually came from. But during this period of global warming, basically the 30s, 40s kicking in, 50s, 60s, 70s, 80s, there was twice as many CMEs as there were now as we're coming out of grand solar maximum, and as there were 100 years ago at the start of the 1900s.
We mentioned grand minimum, but what about the sun's grand maximum? As you just heard, we are exiting it now, and indeed it appears that you have to go all the way back more than 10,000 years to find a grand maximum anything like the one we just had from the 1940s up to the start of this century. Coincidence, I'm sure. Its occurrence concurrent with escalating temperatures.
This is the nice, neat little box and picture of climate science. If you're a mainstream climate scientist, you have the 0.1% varying over the 11-year cycle top-down solar forcing. It's a thermal coupling that starts at the stratosphere and slowly meanders its way down. And everything else that the sun does counts as human forcing. Well, let's take a look at what we can learn from the 600 peer-reviewed papers since 2010. And this is where I'm sort of going to pick up with the most recent stuff. And so we know that there's not just this 0.1% top-down solar forcing in the thermal coupling realm, but there are these oscillation and circulation modulations. Say that a bunch of times fast. And these are also thermal couplings as well. They involve much longer term holding of that energy by the oceans and by the atmosphere. And they do involve albedo a lot more. And these are, again, our thermal couplings. These would be all the papers that show there's a relationship between the sun and El Nino or La Nina, the sun and North Atlantic oscillation, northern annular mode, southern annular mode, even the quasi-biennial oscillation. Pretty much any of these you can think of, they have found these signatures of the solar cycle. But there's also this total vertical column modulation, and this is an electromagnetic coupling, and that is wholly missed by most of the models.
Particles, currents, magnetic fields. These are literally thousands of times harder to model than simple thermal exchanges, and most of their effect is not found in the upper atmosphere, but throughout the atmosphere, and sometimes even the ground, which makes total solar irradiance focus on only the upper atmosphere a major problem.
There is no good argument for ignoring this total vertical column modulation. And so, just to give you guys an idea of what this looks like. So this is mainstream climate science with natural variability from the sun. We have ultraviolet that hits the upper atmosphere and middle atmosphere. It slowly trickles down through global heating, and this is a direct thermal absorption. Now, That little block right there is not going to change. I've just blacked out everything else. And so I'm going to take away the black, realize that the ultraviolet portion is still going to stay there. And so this is what these 600 papers actually show us. That we have, from the cosmic rays and the sun, we have a wide, very broad picture of forcing, particle-wise, in terms of electromagnetic fields, and yes, in terms of the electromagnetic waves as well. And so running down this really quickly, over on the left side, we have the cosmic rays. When it comes to the cosmic rays, or the electromagnetic particles, you can really break these up into the super high energy cosmic nuclei that are created in supernova. Those are the ones that can actually make it down into the mantle. Those are the ones that are absorbed by the silica-rich magma, and we've now seen 3 papers on how cosmic rays trigger explosive volcanic eruptions. The majority of the cosmic rays are really just higher energy protons and some electrons, and those are mostly integrating with the magnetosphere, ionosphere, and performing those breakout cascades when they make it to the upper atmosphere. And then, of course, we have the solar wind, which directly electromagnetically couples with the magnetosphere and ionosphere. And below there in the yellow, you can see that there's that vertical column pressure. And we're going to come back to that. Hopefully, some of you are already getting a picture of what that means. If you can picture when we pull the wind maps, and you can see there really are these circular column cells of unified wind motion. Looking at the electromagnetic waves, there's another side to the right of the ultraviolet. And that would be the X-ray radiation, which is also not included in the climate models. But this is absorbed directly in the ionosphere and upper atmosphere, and that plays a role into the global electric circuit, because the global electric circuit ceiling is the ionosphere, and it has multiple floors, so to speak, at different cloud layers, at the surface, and at a couple of different layers of the crust as well. And so that X-ray radiation, even though it is waveform and it's very much thermally absorbed up at the top, it also has a direct tie-in to the global electric circuit. And so this would be what would be down below here, because the chart doesn't just end right here. So let's take these 2 columns over on the right and come down to the upper level patterns that you really see when it comes to the electromagnetic wave modulation. Specifically the polar vortex events and the jet streams. The jet streams are mostly affected by the absorption of electromagnetic frequencies, mostly X-rays. Those also affect the polar vortices, but also the particles. That would be the X, P, E, N, protons, electrons, neutrons, things like that. And what we see, it's very, very simple. When the sun is blasting hard and giving us a lot of this energy, they're able to take in a lot of this energy. It's a positive correlation. They stay strong. They stay flat, they stay tight. So when the sun is really blasting out, the jet streams are relatively flat. The polar vortex is tight and flat up at the poles. When we lack the solar energy, we start to get this wavy jet stream, and sometimes it can actually wave too hard and lock up on itself in what they call the omega jet stream block, the omega block. And when it happens with the polar vortex, it loosens and becomes really wavy, and when it becomes too wavy, we get these polar vortex events that come down into the States and over Europe and really cause these snow and cold records to fall by the dozens, as we've seen. And of course, so high solar activity is going to mean warmer weather, less extreme weather in terms of what the jets are causing. Weak solar activity means colder events and more extreme precipitation events in terms of the jet stream blocking. That's how you get those areas where it basically just rains for days and days, and it seems like the low pressure cell is stuck there and is just spinning in place. Happened a couple of times in 2011, pretty good. So if you could take the previous cosmic ray column on the left and you could break that down, so we can actually see that there are in fact 3 sources of cosmic rays. There are the cosmic ray nuclei from the galaxy and beyond. There are the solar energetic particles, quite obviously from the sun. And then there are the relativistic electrons from Earth's own Van Allen torus. So like when we get a strong CME compressing the magnetosphere, And it's known that it pushes the Van Allen belts down into the upper atmosphere. We've seen that happen. We've detected it. That's also where the relativistic electrons, some at the same kind of energy levels as some cosmic rays, are penetrating down through the atmosphere as well. When we get high solar activity, it pushes the Hadley cells towards the polar region. This, in turn, pushes the subtropical jet and the polar jets towards the polar region, which is one of the reasons why, whether you're looking at the intertropical convergence zone or the jet stream divide of hot and cold air, you get more of the tropical heat spread to mid-latitudes during the high solar activity when the Hadley cells are trying to expand because they're taking in more of that energy and they're pushing everything a bit towards the poles. And the polar cells, this is really where you have to remember that there are these Birkeland sheets, and the way the European Space Agency drew that, you can't call them Birkeland currents, you have to call them Birkeland sheets. The way they basically come in layers right there around the auroral circle. These are the things that are really interacting with not only the total vertical column of pressure, but the polar cells. So you can see on the left what basically I show up in the atmosphere. And by the way, all I did was reverse the color from NASA's graph. That is NASA's graph. I just reversed the color because I think it's prettier. So we have that motion, but it's not just a motion in place. You see the arrows that are actually on the planet, how they're sort of going in a helix around the world. And so you have to think of that full three-dimensional motion when you're thinking about this. So we have both the motion that you see on, up in the atmosphere. We also have this corkscrewing motion across the planet, and they corkscrew opposite one another, in terms of ferropolar and the ferro and the Hadley cells. And then in addition to these motions, we have the total vertical column of the air that's spinning like this in lows or spinning the other way coming down in the highs. I mentioned the oscillation, circulation, modulation. Another way to say that is the oscillations in the modes, the northern annular mode, southern annular mode. This one is phenomenally easy. We'll start on the right with the quasi-biennial oscillation. High solar activity, decreased effects of the QBO. Low solar activity, increased effects of the QBO. Probably not due to necessarily the sun, but its modulation of cosmic rays. The much more important part of this is there is virtually unanimous agreement among the papers that are out there that the positive/negative phase forcing of high/low solar activity on all of these oscillations, ENSO, NAO, PDO, AMO, NAM, SAM, all of them, it's direct. High solar activity is going to push it towards the positive phase. Low solar activity pushes it towards the negative phase. It is not controlling, but it is also not a coincidence either that the weak El Niños occur when there's low solar activity and the strong El Niños occur during high solar activity. And the opposite for the La Niñas. It's not as though the solar cycle is going to command that El Niños stick around for 4.5, 5 years and La Niña stick around for 4.5, 5 years. Those are going to have their own oscillation. But is it a strong El Niño, a weak El Niño? Why don't you ask the sun what it's going to be? Probably knows better than a lot of statistics that we might otherwise garner here on the planet. So again, mainstream climate science, reality. So a few more notes on some of these things. 0.1% top-down thermal forcing is minimal. It is 0.1% over the solar cycle, and it is slow. The oscillation and circulation modulation is so robust that there is a very wide agreement. Not only are Dr. Tinsley's papers on the North Atlantic Oscillation convincing, but Dr. Leslie Gray's are phenomenally convincing as well. Considerable effects there, but again, those are slow and many of those lag. So for example, I think on the El Nino and La Nina, there's a 1 to 3 year lag from the peak of the sunspots or the minimum of the sunspots to when you actually see it. But when we talk about that total vertical column modulation, that electromagnetic coupling, it is strong. And it is immediate. You guys might remember from the book, it was 3 times confirmed. Some of the ground readings were changing as the solar wind was changing. It is immediate, pretty much, like within minutes. Nothing, no 1 to 3 year time lag like with El Nino. No, well, if you're talking about grand solar maximum versus grand solar minimum, no potentially 30-year heat lag coming back out of the ocean. This is strong. This is immediate. It's not just cloud cover. Dr. Tinsley has some work on basically immediate pressure effects down at the ground as well. And this makes sense because it's a global electric circuit.
So the history of the sun weather climate studies goes back a long, long way. And over 200 years ago, Sir William Herschel, the great astronomer, noticed that the price of wheat on the London stock market went up and down on an 11-year cycle, which was synchronized with the sun. Well, he published those results, but unfortunately he coupled it with an explanation that turned out to be wrong. He thought the sun was getting sick when it had more sunspots, and so the heat coming to the earth was less, and that was why there were poor winters and poor grain harvests. So that tells us a lesson right off that you don't really want to couple your observational basis with a theory unless you've got a good, solid basis in physics and chemistry and a robust model. And unless we have a mechanism, all the skeptics are going to jump in. And Monin in 1972 said, people who talk about this produce an impression of successful experiments in autosuggestion. They're convincing themselves they've found something that's not real. Now, Joel Levine at a NASA conference said that scientists are not going to accept it, the presence of this connection in the absence of an accepted physical mechanism. Walter Roberts said the same thing. But just a month ago, a paper came out in Nature Geosciences by Chiodo et al. The paper was saying that these correlations were not real, of the North Atlantic Oscillation were not real, and they were interviewed, and the headline of the interview said that the connection had been debunked. And then they used a sophisticated climate model to show that the leading candidate for a mechanism, which was the solar ultraviolet, there wasn't enough effect.
And it's true. When you just look at the irradiance taken at the top of the sky, there isn't enough to account for the modulations of the climate. But the purely electrodynamic component of space weather largely integrates with the geomagnetic field of Earth, coupling and funneling towards the polar region. The compression on the day side pushes ionosphere electrification, and that ionosphere works down through the global electric circuit, a constant and forever operating electrical atmosphere with both altitude and pressure determined character. That pressure pattern is simple, by the way, and a key clue to the mechanism.
The current comes down in fair weather high pressure, goes back up in not just out of the low pressure, but all along that line that comes, one of the arms that comes out of a low pressure cell where the winds are crashing together, and you basically get a line of storms. In fact, that's how most tornadoes form in the U.S. They don't form in the circle of the low. They form off the tail that comes off that converging wind area. All along those areas, all along those thunderstorm regions, the current's going back up and returning to the ionosphere. And so another thing that they will eventually, once they get over the gravity of the cosmic rays and the particle forcing, and they expand particle forcing to include high energy protons and other things like that. I'm glad somebody got that. They might want to think about the effect of electric current going through a resistive atmosphere in terms of heating. Because I asked a couple of climate scientists, well, how much of the global electric circuit, resistive heating in the atmosphere, do you take into account? And the answer is there is none. What? Well, there's none in the models. So I don't know which one of those top two equations somebody's eventually going to want to use, but all the information is there to figure out exactly how much heat is caused by the electric currents of the global electric circuit.
So the short-term effects seem to be consistent with some ideas that were floating around in the 1980s about atmospheric electricity connecting near-Earth space environment, where space weather occurs, down through the atmosphere with the surface and with clouds. The global electric circuit has been known, since even before the time of Benjamin Franklin did his experiments on thunderstorms, and also in fair weather. You can fly a kite in fair weather and it'll cause electric discharge if you have a conductor coming down from the kite. And the reason is that the thunderstorms, they actually send current upwards to the ionosphere because the conductivity increases as you get higher up. So it's easier for the current to go up to the ionosphere than to go back down and around to the bottom of the thunderstorm. So what's happening is we're getting this downward current JZ, which varies as all of these things, as VI varies, and there are several solar wind inputs that will vary VI, and as RM varies and RT varies, and there's several solar wind inputs that will vary these parameters as well. So we get all these variations in the current density that have different signatures in latitude and time, and they come down and they charge up clouds. Clouds are like another resistor in the circuit, and so now we've got electric charge in the clouds, and that electric charge then migrates very quickly to the droplets and the aerosol particles, such as condensation nuclei and ice-forming nuclei, and affects the interaction between them. This is the conductivity here, this vertical curve here. Conductivity, as you come into the cloud, the conductivity drops by a factor of 3 in this case. We've got a cloud between about 900 meters and 1,200 meters altitude. Conductivity drops in there to maintain the current continuity. The electric field increases. And when you have a gradient in electric field by a very simple and elementary Gauss's law or Poisson's equation, you have to have the presence of excess charge of one sign. You have space charge. And so balloon observations, in fact, showed that you do get negative space charge at the base and positive space charge at the top, as expected from the smooth curve. But there's a lot of structure in it because of turbulence in the cloud. So you'll recognize this diagram. Again, it's a north-south section through the Earth and its magnetic field and the solar wind. And we've got these cusp regions where the field lines from near the magnetic poles there, considered open field lines, they map out and they can merge in with the solar wind in complicated fashions here. So we have an east-west electric field which drives these auroral currents that produce what's called the auroral electrojet, in addition to field line currents here. So there's a lot of complicated plasma physics going on there, but if you just measure the potential of the ionosphere above in the region of the south magnetic pole and the north magnetic pole, you can fly a satellite through it and look at the potential difference with respect to the low latitude regions, as has been done many thousands of times. You can use the super-down radar to look at the drift motions of the plasma. You find that this is a diagram from Mei Lam and her colleagues at the British Antarctic Institute that was published in 2013. The potential in Antarctica goes positive when you have a positive BY by up to about 25 kilovolts. At the same time, the potential within the polar cap in the northern polar cap goes down by about 25 kilovolts. And of course, changing the ionospheric potential in this way is superimposing it on the 250,000 volts, the 250 kilovolts that we have from the thunderstorms, and that changes the current coming down to the surface, and that can be detected by electric field meters at the surface. With Forbush decreases, which are decreases by 10 to 20%, Todd and Niverton, way back in 2001, showed that the cloud cover decreases by tens of percent in this region within the polar cap. Now, cloud cover changes were observed by Pudovkin and Veretnenko here and with the Russian ozone observing network, and they found that cloud cover, or at least atmospheric transparency, decreased when you had Forbush decreases. This is a paper we published in 2013. What happens to the collision rate coefficient, which you can see here is changing by orders of magnitude as we go up this vertical scale. And this is the size of the particles, so we go from a nanometer up to 10 microns. So we call this electro-anti-scavenging, which I think is occurring in these regions. A summary, if you like, a flowchart of what's going on. On the day-to-day timescales, We see thunderstorms. This is our control. The thunderstorms change the global ionospheric potential, and we see changes in the Arctic and Antarctic clouds and the surface pressures. Two categories of solar wind inputs to the global electric circuit: changes in ionospheric potential and changes in atmospheric conductivity, and they do that on the day-to-day, decadal, and longer timescales.
As a blast from the sun approaches the magnetic field, impacts, compresses the day side, and forces energizing of the ionosphere, that potential is going to come down, mostly in the high-pressure atmosphere electric columns, and deposits in atmospheric boundary layers, into clouds, and into the ground as well. It is believed that cumulonimbus clouds may stir this potential in the ground to help juice up their lightning and fuel their growth via static attraction of dust and vapor particles. Indeed, the energy will mostly flow to the high-pressure cells, read here, where it not only deposits but then follows the vapor in the wind out to the low-pressure cells to rejoin at the surface layer, or in whatever layer they deposited, where the low pressure sucks in, and then forming the tubular column up through the sky at the cloud layers, and then depositing that at the jet stream and above to complete the circuit.
As we heard from Dr. Tinsley, and I'll just sort of quickly say it again here, there's a couple of ways that they affect clouds, and they both sort of point to more clouds, and that is the direct creation, really, of cloud condensation nuclei out of existing particles that might already be cloud condensation nuclei if you've given them enough time, but you whack them with a cosmic ray, and all of a sudden they're attracting dust and water vapor and other things that like electricity. And the other thing it does is it ionizes the ambient air if it doesn't directly hit one of those aerosols, such that that ionized air is ready to go find those aerosols. And they are attracting water vapor, and they are attracting dust, just like the Swiffer sweeper works in your home. It's the same, it's basic principle between the dust and the vapor up there. And so I actually like the way Dr. Tinsley put it much better than this, but it helps particle nucleation, and it helps the particle ionization up there.
Following 200 papers in 5 years correlating solar activity to climate out of China and India, Princeton took a harder look at cloud cooling potential and cloud fraction data in history. Their initial proclamation that the entirety of climate science misunderstood the cloud effect didn't even mention the sun or cosmic rays, but its truth re-energized the researchers around the world who already knew what drives the clouds. From universities across the United States to researchers in Canada, Europe, Israel, have now come a tsunami of papers in the last 24 months which seek to jerk the wheel of climate science, all while Yale leads the charge of nearly 36 universities tracking the cooling effect of icebergs and the potential cold climate bomb they can unleash on the world. Meanwhile, the official climate group has had no choice but to bend to an overwhelming totality of the space weather forcing evidence.
Here cometh CMIP6, and for the first time ever, cosmic rays and medium energy electrons are going to be included.
Well, sort of. It should be called partial particle forcing, since the cosmic rays are only part of the story, albeit a critical one for cloud studies, and medium energy electrons are not very telling of the highest energy particles, or the proton events or geomagnetic storms, interplanetary magnetic fields, or the daily flux of the solar wind. It is egregiously under-inclusive, much like total solar irradiance, but also there's no allowance for threshold event analyses in these datasets. It's like studying chicken. Imagine you studied the chicken for harmful bacteria at 0 degrees, 1 degree, 2, 3, 4, and then all the way up to 150. That is a lot of trial runs, and you would conclude that temperature has no effect on chicken safety. Of course, you would be wrong. If you just looked a bit outside your box, you would find that around 165 degrees, everything changes, and the situation cannot be undone either. It's not going back to that pink color, and those bacteria aren't coming back from the dead. Once you hit that threshold event, the situation changes entirely. This is what happens with major solar storms or major cosmic ray events, and which is still missing from the models. Furthermore, there has been a nearly complete refusal to use the particle forcing dataset that does exist. Most of the studies on climate still today do not mention the sun, or they use the total solar irradiance instead of the particle forcing, partial particle forcing dataset. The few studies that attempt to correlate the major threshold events to hurricanes or earthquakes are written off almost immediately, despite a direct electromagnetic connection through the global electric circuit from the sun to the crust.
Two categories of solar wind inputs to the global electric circuit: changes in ionospheric potential and changes in atmospheric conductivity, and they do that on the day-to-day, decadal, and longer timescales.
Hundreds of studies, equations of Joule heating in the atmosphere, corrections of cloud understanding, all pressing forward as long-term solar trends of the grand cycle cast a more ominous shadow over the concept that its effects on climate are minimal. In addition to knowing that the 1900s saw the highest solar activity of the last 11,000 years, we see the Roman warming period lining up with a relatively strong grand maximum. The mini ice age was from around 1400 to 1700, and of course, that then brings us back up to modern super grand maximum and the time of global warming. Another of the flawed foundations, and one that fills in the blanks for solar forcing through time and periodically overrules everything else in the climate.
This is how climate science determines what high volcanic forcing is versus what low volcanic forcing is. The problem is that this data selection does not tell you what high volcanic forcing is, because this entire timeline right here is contained within the little green bars over there on the right in the paleoclimate data. It's always amazing. They have this data that goes back, and yet climate science won't use it. So we have very, very real volcanic forcing back in the day, if I can put it that way, back into deep antiquity, as Dr. Peratt would put it. And literally, take a look at this, that little bit down there on the right. That's this right here. That's all that is. And so this does not give us an adequate representation whatsoever of what high versus low volcanic forcing is. In fact, things can get a lot realer. I've lined up some isotope records here with this, and of course you've got the medieval warm period. A little more than 1,000 years ago, we had the mini ice age, or the little ice age, whatever you want to call it, that occurred in the wake of that high volcanic forcing, and in the wake of not only the Maunder minimum of the 1600s, but a lot of people fail to remember the previous grand solar cycle was a dud entirely. Yeah, the Maunder minimum was the low point of that, but the entire 400 years before that was a dud. It was like a continuous 600, not really 600, but 400 to 500 year grand solar minimum for the most part. And of course we see grand solar maximum rise up through the 18 and 1900s, peaking somewhere between 1950 and 2005, while we see record low stratospheric aerosols, not just in the climate era, but back through much of paleoclimate data. You might remember when Dr. Tony Phillips shared that presentation that it was only presented as an abstract at the conference, but Tony Phillips got permission to post it on his website, and it showed, just based on the visibility of the lunar eclipses, that we are indeed at a record low, pretty much, for stratospheric aerosols if you're looking over the long term.
It gets better. Not only are these foundations of modern climate science flawed, not only are they key pillars in the understanding of the larger equation and bigger picture, but solar and cosmic particles interact with volcanic aerosols to enhance these correlations.
With my student Matt Kirkland, we looked at how the solar wind speed actually varied as we went across the boundaries between these high speed and low solar wind speed sectors, and or magnetic sectors. And the solar wind speed drops in the low speed region here. We're going from 20 days before the crossing of the boundary to 25 days afterwards. And the relativistic electron flux measured out at geosynchronous orbit also drops quite dramatically, actually, by several tens of %. And this measure of the storminess in the North Atlantic, well, actually this is a global measure of storminess of winter storms, and the storminess is measured by the vorticity, the rate at which they're rotating, or rate at which they're rotating above a certain threshold of rotation within a certain area. This measures the area over the total northern hemisphere that winter storms are causing high rotation rates. And that dropped too, in synchronism with the drop in relativistic electron flux. Now, these data are all for high concentration of stratospheric aerosols from Agang and Helka from 64 to 70, from El Chicon 83 to 86, and Pinatubo 92 to 94.
And so let's take a look at what happens when the sun fires off and when the sun affects Earth in terms of the tropical activity. The KP8, the level 4 geomagnetic storm of this summer, was followed just days later by 6 cyclones popping up in the Pacific. And that one just to the northeast of Hawaii did not hit the requisite strength to be classified in this way, or else it would have been the first time in recorded history of there being 7 in the Pacific. As I mentioned earlier, this was also the earliest example of 3 typhoons forming in the Western Pacific. In 2013, we had an X-class flare and magnetic crochet, very rare event. This is when the solar flare is so powerful that strong electric currents actually get surged through Earth's atmosphere. Now, this happens when the CME impacts Earth. The auroral electrojet starts firing up with the northern lights, and that induces currents. And just days later, we have Typhoon Haiyan. Now, when you talk about the typhoon records that are the big boys, you know, strongest storm, lowest pressure, fastest winds, largest area, every single one of those big-time typhoon records are held by either Haiyan or Typhoon Tip, which occurred in October at the exact peak of sunspot activity back in 1979. And although we don't know what the flaring was like, we have some idea of what the auroras were like, we can say definitively that for the year 1979, statistically, the greatest chances for significant space weather occurred at the exact time Typhoon Tip formed. So, can you guys all see the timestamp down there? Is that sticking out to you guys at all? So we had very, very quiet space weather actually for days and days and days. And then, all of a sudden, the sun woke up like crazy. A ton of CMEs. Now, none of them were coming at Earth, but these were the type of tight, coiled CMEs that you often see really perturbing the inner heliosphere. And of course, this occurred, as I heard somebody say, exactly at the start of Hurricane Katrina. And it ended right about the time it hit its peak strength. The last time we had an X10 solar flare or higher was just a few days after that event that caused Katrina, and that was an X17. And the mid-month storm outbreak was the very last time before this summer that we had 5 Pacific cyclones at the exact same time. A very significant outbreak. The last time we had a near major solar flare was an X9 in 2006. We had the Hanukkah Eve cyclone strike Washington. If anybody's familiar with that, it was one of the strongest storms to ever hit the state of Washington. And to set a rain record in Seattle is no small feat, I have to tell you. Interestingly, that sort of very odd track that Hanukkah Eve storm took is very similar to Oho, which formed at the exact same time as Joaquin and the Metacane. And this is what Dr. Uyen mentioned, and it took a track that was very, very similar to the Hanukkah Eve storm. It hit the Canadian coastline a bit further north, but it's very interesting to see 2 very rare storms, and this late in the season, you don't see a Pacific hurricane swing up and go at BC like that, British Columbia, and we've seen it twice immediately after significant solar events. Hurricane Sandy. This was about the only solar uptick for about a month before or after Hurricane Sandy. And it just sort of came and went in the period of a week, where out of nowhere we jumped up from B and C class flares up to M and X class solar flares, including a very large coronal mass ejection, which was not aimed at Earth, but as we've learned, they don't have to be aimed at Earth to perturb us. And that was, of course, when Hurricane Sandy sort of came up and did its thing, and it was the largest Atlantic storm ever by gale diameter. So, let's come back to this. And I was speculating that the melted power line and the electrical explosion just a few miles away in Washington state, along with the transformer fire in India, were very good candidates for space weather-induced disruptions on the ground. Now, wouldn't it be great if we didn't have to speculate, if the atmosphere could give us a hint, anything to tell us that, hey, wait a minute, yes, there is a disruption in that particular part of the world, Washington state and India? Well, Mumbai is where the transformer blew, is directly to the east of that cyclone that formed that day in the northwest Indian Ocean, and that was the tropical storm we just mentioned coming up towards British Columbia. Those were, at that time, two of the more significant tropical events on the planet, and just to the east of each of them is where we saw the best candidates for the space weather-induced activity.
That full presentation back in 2015 covered many more events, but now let's jump to September 2017 once again. This was the next time the sun got really active after 2015, and it was an unexpected flurry amidst months of quiet. But it surged X-rays, high-energy proton radiation storms, intense solar wind impacts, and tremendous geomagnetic storm activity. When the first sunspot appeared, Hurricane Harvey ran ashore in Texas, and by the time the major flares were occurring, the hurricanes were surging as well. Irma, Maria, Puerto Rico devastated, Panhandle and Georgia hit hard. It was the last great solar uptick we have had, and in 2019 thus far, the sun has been tremendously inactive, but it is showing signs of coming back to life for another sunspot cycle maximum, set to gear up in the next few months. Now, while we seek here to address the foundations underlying the thousands of climate studies, there are already a considerable contingent of those who cry foul at those climate studies themselves, from the rigged models to grant fund baiting and blatant data tampering, whistleblowers from inside the government. And there are a number of key websites to track during this true shift in what is nothing short of a political science. And now back to that science, because up next, a paradox. A seemingly backwards truth that has been demonstrated in numerous studies the last few years, and which was crazily depicted over a 4-day span in the movie The Day After Tomorrow. To keep it simple, when the ice is locked at the poles, we have proper ocean salinity and temperate climate in mid and low latitudes. But when that ice begins to melt, it freshens the oceans and cools them. Since the poles receive no sunlight in winter, the region gains new ice only to amplify the same cooling and freshening processes the next spring. And as the glaciers melt and slide into the sea, and as the icebergs break off, tremendous amounts of that cold, fresh water not only surround the polar region, gearing up for a major freeze event that overcomes the spring with its sunlight reflection, called albedo, but they are distributed throughout the globe as well. While this helps alleviate any acidity problems that crop up in the oceans, it does not help support the salinity and temperature picture required by the mainstream narrative. This is another threshold event, when the oceans are so chilled and desalinated that they are unable to sustain their phase in winter, unable to support the global oceanic circulation, and they freeze to incredible latitudes, causing extreme albedo in the spring and extra cool freshwater melt in the summer. At this threshold event, kinetic energy and chemistry work to change the reflectivity profile and water phase preference of the planet, which it has a very easy way of correcting. The cold is not hard to trigger, and once it is here, it is hard to break. The Earth is not usually a temperate planet with tropical equatorial zones, at least not anymore. Long after when we think the dinosaurs died, something set in an approximately 100,000 year cycle, where the most important numbers compare the interglacial warm periods to the glacial areas which last for a much longer time. We are currently in an interglacial with nice warm temperatures. We are very much towards the longer end of time within it when we look at how long we've spent in past ones, and sooner or later, the Earth is going to throw more than a 10-degree drop in temperature across the planet, with high latitude regions seeing 20 to 30 degree drops in temperature. This is compared to the maximum global warming seen thus far of about 1 degree during the current record-strong El Niño year. The simple fact of the matter is that we only get so much time with the planet like this, and then we're heading back into an ice age. As I said at the beginning, we need to stop pollution, and the number one reason is that this is the air we breathe, the water we drink, and the soil in which we grow our food. We cannot poison them. But we must also not ignore the flaws in the foundations of the entirety of climate science. No existing study is immune to these flaws, not one, and it's because they all did what they were supposed to do, use the best assumptions and guesses and models available at the time. It's just that they are demonstrably wrong. They misrepresent a 1 degree increase in temperature, while 10 times the cold fury is arguably overdue for our planet. The sun was at an 11,000 year peak for that 1 degree of warming, and volcanic cooling at record low. The sun is due for a grand minimum this century. Earth's magnetic field is enduring a long-term weakening event, both of which mean more cosmic ray cloud forcing, more cooling of the planet, and all with the 100,000 year ice age cycle staring at us from history, seeing the world currently looking the other way, watching as the sun prepares for a restful beginning of another grand cycle, and she whispers to herself, "It's almost time."
The number of publications varies with the level of respectability given to the field, which, as you can see, goes up and down. And this is only up to 1992. There were over 2,000 publications up to 1992. There's also been more than 20 books published on the subject of sun, weather, and climate interactions.
Data selection matters. And no, I'm not just referring to everything I was just talking about for the last 40 minutes. So let's take a look at some data selection and where it really matters here. So, climate.gov. So we're going to actually look down there where, in the bottom panel there, where they have the spring snow cover. And indeed, spring snow cover is on the decline. I've gone ahead and zoomed in on this here, and I've even gone ahead and I've drawn a regression line for you there. The problem is, and as this comes from the Rutgers Snow Lab, obviously Rutgers University, this is their graph for the winter snow extent, and this is their graph for the fall snow extent. Yeah, it's true. We have less snow in the spring. We have more in the winter. We have more in the fall. Data selection really matters.